we're on the home stretch, and which is a good thing. We've these are going to be the last 3 now or never lectures. Before I get into the first one of those, which is expansive and collapsible soils, I want to, usually this is the time of the semester when I kind of get off the subject and deal with some issues of broader interest. And one of those issues is graduate school. In the mid-1990s, our glorious society, the American Society of Civil Engineers, commissioned a study on whether or not we should make the graduate, at least a master's degree, the entry degree for the profession. And one of the main movers and shakers with this was the University of Wisconsin at Madison academic named Jeffrey Russell. And the idea was that since doctors have to come in with a graduate degree and attorneys have to go in with graduate degrees, and these are respective professions, the engineering profession would gain more respect if we required that our practitioners have, and professionals, we are trained to be professionals after all, have a graduate degree of some kind. And the committee basically came to the conclusion that yes, we should be moving and eventually arrive in that direction. That was a long time ago. The states and their licensing, which really control this issue more than anybody, have not really moved in that direction. One of the reasons why I chose engineering, in addition to a long family history of engineers and technically trained people, was because I could get a job after I got out in industry, which I'm sure many of you share that desire, particularly now with the fact that most students graduate with a decent amount or an excessive amount of debt. And so it's not really, it's not an absolute, you can get still get your engineer's license with, your degree, passing the FE exam, which is a prerequisite for some employers like TDOT, getting your 4 years of experience under a professional engineer, and then, or more than one actually, and then sitting for your PE exam, after that, and then you get your license, and then you have a continuing education requirement. And so therefore, it's not an absolute necessity to get started in your career with a graduate degree. However, my experience, both as an academic, as someone in industry, tells me that it's necessary to get in the profession. I believe that sooner or later, as you work through your career, you will find graduate school to be a more attractive proposition in terms of your own advancement. It is simply impossible, particularly in state institutions which limit the number of credit hours before they give you the graduate you. Allow, it simply isn't time to cover many topics, and I've grazed over a few of those topics in the course of this course, and certainly in soil mechanics, and for that matter in fluid mechanics lab, all 3 of them. So stuff that I would have been nice to have found out as an undergraduate, but I didn't, because it just wasn't part of the curriculum. Some of that was due to the time I took it, and some of that was due to the nature of the curriculum itself. So that having been said, I think graduate school is something you need to keep in the back of your mind as you move forward. Some of you will want to, or particularly those of you who want to pursue a career in academia, will want to do it immediately. Some of you will have an opportunity to pursue, particularly with the online options available, will want to pursue it sooner. Some will take longer. My advice in the timing, though, is that don't wait as long as I did. I waited almost 20 years to get my master's degree and another 20 years to get my PhD. And I want to talk about that little saga for a minute because it took place at this institution and with involved people, many of whom my students know. And of course, those of you from the outside, this is sort of an outside looking in, but 10 years ago this fall, my department head, Dr. Joe Wino, and Dr. Ignatius Falmanung sat me down and asked me to get my PhD. And their idea was that I was able to teach more courses if I had my PhD. And I said yes, I would do this. It took a year to get the PhD program at UTC to warm up to the idea. But I started in 2011, and 5 years later, after a long process, and the PhD is much longer than a master's degree. I did my master's degree and doing part-time in 3 years. It took 5 to get the PhD. And part of my work was actually at UTC. Well, a lot of my work was at UTC. And it was quite an epic. And actually, the way it worked out was I was officially awarded my degree in August. And what that meant was, because of the way that our Soil Mechanics and Foundations is structured, my spring semester students had me with just a master's degree, and then in the fall had me as a PhD. And that kind of mixed things up a little bit. I think it was a real, it was really kind of a wake up for them. And I have a little piece I've had on my website for some time that comes from that era called Mirroring Our Creator. And I linked to it from the video. I encourage you to look at it in terms of how I view not only how I view my students, what my expectations. I'm not a typical academic in any sense of the word. Many academics, like to, really, appreciate the really good students. I try to be a servant to all of them and to bring the best out in all of them. And the reasons why I do that, I explain in Mirroring Our Creator. I actually finally got to walk the class. Currently, the COVID crisis has messed up this year's graduation, but I actually got to walk in December, and UTC's own Yancey Freeman gave us our send-off, a commencement address, and part of his commencement address was quoting Proverbs 3, 5, and 6. And with that send-off, I was done with that and moved on to where we're at now. So I encourage you to look at some of that. Now we turn to what this particular chart comes from NAFAC DM7, called special materials. And special materials are those materials which are well, they're really, it's a nice way of putting materials that can be a real pain in the rear end. And they're going to talk about, and we're going to talk about some of those. I've talked about some of them before. First one they talk about is quick clay, and we talk about those are the other way of calling those is sensitive clays, where moving and remolding the clay results in a catastrophic decrease of strength. And you see some of these in marine, but also in your upper latitudes, Scandinavia, Canada, and places like that. Hydraulic fills. Hydraulic fills was a cute idea that we had a long time ago, where we could just simply take dirt, mix it with water, pump it somewhere, dirt dries out somewhat, and we have a fill. Hydraulic fills, there was a major collapse with hydraulic fills, and that pretty much ended their career. But I will say that inadequately compacted fill, be it hydraulic or otherwise, is a major source of problem and trouble in geotech. Then we have collapsing soils, and we'll talk about those today for sure. The main one are your low S soils, and we mentioned this in soil mechanics. These are aeolian soils, and aeolian soils is a fancy term for soils that fly through the air and are deposited that way. They are soils which, on the one hand, you can cut them vertically. They can produce some very rugged terrain, something I did not really fully grasp until I visited the year before last the Vicksburg battlefield and saw how rugged it really looked for an area which we usually think of as flat. But they're also subject to collapse, and that has to be taken into consideration. The next one we have are your submarine soils. Some of your marine soils can be nasty. The one that has, in my career, I've seen most of is calcareous soils. And in fact, I did some work, speaking at Vicksburg, for the U.S. Army Corps of Engineers Waterways Experiment Station in the 1990s related to their experience with calcareous soils and pile driving. And I've got some of that on my website. That they are unpredictable. They tend to either they are subject to some very sudden remolding, and they can actually experience the collapse of their own kind. They can also experience, they're very tricky soils. Calcareous soils are actually the deposits of living coral reefs, and they can be serious trouble, as is the case with virtually any carbon-based soil, like limestones, where you've got the karst topography we have in this area. And then there's lateritic soils, which are the result of mostly tropical weather and its chemical interaction with the soil. And that's a complicated subject. Lateritic soils are mostly in the tropics. The one notable exceptions are parts of the southeast, South Georgia, Alabama, that area. You get that deep Georgia clay, that's a lateritic soil. And that is a testament to the oxidation that takes place for lateritic soils. Limestone and coral, I've already talked about those. One soil that was not listed here let me make sure that I didn't miss something. I did not. It's expansive soils, and we're going to talk about those also. Let's talk about, I'm going to stick with mostly collapsible and expansive soils. Collapsible soils are soils that are subject to large volume decreases, and if your volume decreases, then whatever is on top of it is going to go down in a hurry. One of the irritating things about this topic and expansive soils is most books do a lot of qualitative stuff on the subject, but they don't do much quantitative stuff. I've tried to fix that, particularly with the expansive side. But basically, we need to be able to have some way of predicting collapsible soils. Now, obviously, there are laboratory tests that can do that. But a quick and dirty method is shown right here, where you have liquid limit here and dry unit weight. As soil's dry unit weight decreases and the liquid limit likewise decrease, you have a greater potential for collapse potential. Obviously, that's going to vary with the specific gravity, but not much, because the specific gravity of the soil particles outside of organic soils doesn't vary much. So you have two distinct regions. If you know your liquid limit and your dry unit weight, you can get some idea whether your soil has collapsed, but whether a soil is collapsible or not. And then we have this thing called the collapse potential, and can be determined experimentally. How do you deal with them? For shallow foundations, suitable to grade beams help to distribute these and mitigate the effects of uneven collapse. One of the things about collapsible soils and expansive soils, to some extent, are subject to the same problem. You have the issue of the water content is different, and soils, of course, vary in and of themselves, and you will get major differential settlements if you do not do something to mitigate those. And one way, of course, is to stiffen the structure so that in case certain parts of the foundations, the spread footings experience major differential settlements due to collapse, and others don't, that the whole thing will stay even. And grade beams are one way of dealing with that problem. With deep foundations, of course, if you can actually get past the collapsible soil and get down to a more suitable stratum, then that is a solution. Deep foundations provide that. Expansive soils. Most expansive soils are Montmorillonite clays. And Montmorillonite clays are named after a place called Montmorillon in France, where they were first identified. I'm not sure about discovered. I think people have been, with soil, with soil mechanics, people have been dealing with problems for millennia that they really didn't understand and didn't have a good scientific grasp of. But nevertheless, they dealt with it many times successfully. There are different. I'm going to talk about, it talks about a figure in the Kane geotechnics. We're going to talk about how, in fact, it's this one. This is the old Casa Grande plasticity chart. Just when you thought you had left this behind in soil mechanics, here it rears its ugly head. But it can be useful because Montmorillonites tend to live on the up towards the U line, up here. And as a result, if you get this combination between your liquid limit and your plasticity index, you probably have a Montmorillonite clay. If you've got a Montmorillonite clay, you need to watch for an expansive soil. So with that in mind, you have a couple. So that gives you an indicator. In fact, to a large extent, soil mechanics and foundation general is kind of a detective work. And the reason why we have these indicators is to signal, without having to go through a lot of fancy laboratory tests, you may have a problem. Don't ignore those when you're actually analyzing your data. We have simple, with the collapsible soils, we have, dry unit weight and the liquid limit. Here we have liquid limit. The Atterberg test. Very fundamental. This is another great thing the Atterberg test does. It gives us a signal that we need to pay attention to what's going on. That's one reason why we like these tests. These tests not only sometimes will give us hard data on what the soil's properties are, but sometimes they'll give us, flashing indicators about, you need to look at this. At this point, we want to stop and define a quantity called the activity index. And the activity index is given in your book, and it shows here. It is the ratio, the plasticity index of a soil to the proportion of a soil which is less than 0.002 millimeters. And that's not a typo, by the way. Those are very small particles, but those very small particles very much help to drive whether a soil is expansive or not. And the relationship between those two is for activity. The higher the activity index, the more we can expect soils to swell. The lower the activity index, the less they're prone to swell. And by the way, in this chart, which I referred to before, it gives us some typical values for montmorillonites. You see that sodium-based montmorillonites are the highest activity index, and it decreases from there. And these soils can be very difficult to deal with. There's also, since we were dealing with the activity index, just when we thought it was safe to go out again, we have the modified activity index, which is over here, also in your book, which is PI over CF minus 5, which CF is expressed and PI are both expressed in percentages, both of them. And so therefore we'd simply knock off 5% off the CF to get a modified activity index. So we're going to see how both of those work in just a minute. The activity index is a good indicator of how expansive a soil will be under changes in water content. These are regions where you find expansive soils. The damage to these things can be considerable. If your soil is constantly expanding and contracting under your foundation, it's going to create stresses, particularly and almost inevitably if it's not even. And usually it isn't, because the water content changes under a structure are not even. And so you can get a great deal of differential settlement if your water content, say your soil is perfectly homogeneous under a foundation. If the water content changes towards the edges and is constant in the middle, then you're going to get a constant, up and down push along the edges. And that creates differential settlements and enormous damage to your to your foundation. It can be very destructive. One thing about swell potential is that once we translate the activity index into swell potential, and we do that, and there's a number of ways. There's a couple of ways we're going to look at doing that. This is where the qualitative versus quantitative thing gets kind of a little bit messy. This chart in your book is your percent clay sizes, which are finer than 0.002 millimeter, the CF basically, and the modified activity index. And you'll see that if we combine these two, we can have low swell potential, medium swell potential, and of course these are all defined as low, as the board between low and medium is a swell potential of 1.5%. The swell potential for between medium and high is 5%, and to go to very high, between high and very high, is 25%. These are indications of how much a soil will swell. That's good. The problem with this diagram is it doesn't really give me a direct way of computing those. And by the way, we're only scratching the surface. This topic has been explored extensively, and there are quite a few different correlations that have been developed to estimate how much a soil will swell. Unfortunately, I don't believe that the problem with this, it gives you an idea how much it will swell, but it doesn't really tell you, it doesn't really translate that. I'm going to show you a method, a fairly simple and fairly well accepted method that actually does that. And this is a determination of actual soil expansion. What we do is we take under the foundation slab, you have a wet profile and a dry profile of pore water pressure. And we basically determine where, for example, if we say that this varies between 10 and 20 feet, then we need to evaluate this at 10 feet and evaluate it at 20 feet and come up with what's different between the two. The question is, how do we do that? And this is a sort of an overview of the basis for the calculations, but the method I'm going to teach you to use for that is van der Merwe's method. Van der Merwe was from South Africa and developed this in the early 1960s. And basically what he did was the following. You've seen this chart before. It's very similar in concept, at least, to, well, it's a little, and actually gives you very much the same kind of as to this one, percent clay versus activity index. Instead of that, it uses percent of clay to the plasticity index. That's probably a little bit more sensible approach, because the activity index is dependent upon the on the CF. We saw that with the equation. So if we get away from that, we have this, and we notice that we have activity is 0.05. The activity index is equal to unity here, and the activity index is equal to 2. And we have these regions of low swell swell potential, and then we have medium swell and high and very high swell potential, and then low is down here. Excuse me. Low is right here. We don't worry about anything below a half. Low, medium, high, and very high. And what we do is we take a soil's properties, we locate it in there, we determine the swell potential, and then we use that to calculate what the actual change in height. Kind of like a reverse consolidation problem, where in the consolidation problem we determine delta H going this way. In the swell potential, we determine it going this way. And this is the basic equation we use for van der Merwe's method. And then we have the A delta H, total change in heights, the layer index, which is assumes that we divide up. If you've got a situation like this, where we have several change, water table changes and whatnot, we need to find out, for example, if we want to go between 10 and 20, say this is 20 feet and 10 feet is here, we want to find out the swell potential change right here. And we might want to divide that up into a couple layers, something like that, and determine that. Because that's where all the action is going to take place. That's where our change in height is going to take place, is where the water content changes. And then total number of, or even in some cases, for example, let's say we got really wild swings in water. It goes from 20 feet up to 0, which is possible, all up to the surface. You get changes in swell, in water table. You'll get whoops, I'm overshot. Okay, then we have inverse swell potential. Now, the reason why I reformulated this, I put the inverse potential down here, and I did that primarily for ease of computations. Because if you flip that, there are two problems with the way that van der Merwe's method was formulated in the first place. First of all, it was formulated strictly on what were then called imperial units, which were basically similar to the units we use in the United States with a few minor differences, long versus short tons and all that, but they were used in the British Empire. The Brits abandoned those for the SI system for the most part, and they millimetered their way to the SI system is what they did. And they, and as a result, the formula that you have, that most textbooks who actually cover this give you, is not unit friendly. So I have reformulated this, and I have a little piece on my website which discusses that particular issue, where if I go from here up to here and over, in other words, if I pick a combination somewhere, I can immediately relate it to a definite number here. And then if it's infinity low, obviously infinity, this goes to 0, you don't have any problem. So, and then the thickness of the layer, and then there is one other thing with van der Merwe's method, and that is the F by the reduction in the reduction factor. That was something else that he had strictly in feet. I also have a form in meters as well here. So you're pretty much it's pretty much a plug and chug once you've done your layer, and it's done on a layer by layer basis. How you pick your layering will have some influence on the answer. So let's take an example. Given a clay soil with a PI is equal to 40 and CF is equal to 55, find the swell potential and amount of the vertical movement, assuming only 1 meter of soil is significant. In other words, that's where you have your water change. So that's, and actually I think we're assuming that it's the top layer. I think that's one thing I didn't put in here, that the top layer of the 1 meter of soil is at the very top, at the surface. So first I want to compute my swell, my activity indices. That's pretty simple. PI over CF is 0.72. Both of them are percentages. Make sure you get that. Otherwise, if you get a number, if one of them's not percentage, you're off by a factor of 100, and that's no fun. And then modified activity index is equal to PI over CF minus 5 is 0.8. So in this case, they're not that far apart. There are two ways of doing the swell potential. From figure 5.27, it's high, it's about 10%. From van der Merwe's method chart, it's very high. If you're going to use van der Merwe's method, you need to use van der Merwe's chart. And then you plug and chug into this formula, and this shows you exactly how, first of all, the delta D, the meter, and I'm again assuming the top layer, and the reason why that's important is because this is the depth to the center of the top layer. If the top layer is 1 meter, the distance center is a half. So I plug that in there, and I use the metric form of that. I use 12 for very high, and I get 69 millimeters, which, or 6.9 centimeters, is nothing to sneeze at in terms of expansion, change of soil volume. So that gives you an idea of why in some soils this is very important. These are not unreasonable values to use. Foundations for expansive soils. There are many ways of dealing with problems like this. One way, of course, is this one, where we actually we have these slabs, and then we got these voids. And basically the way we do it, and we leave some kind of venting system, we allow the soil to swell and shrink under the foundation while not compromising down here basically the load bearing of the foundation. We allow the soil. If it takes deeper foundations, we can obviously go with, and we're going to talk about using drill shafts in just a minute. We can talk about that. there are other methods to use. One thing that is a good idea, swelling and expansion, swelling and shrinking of these soils is varying the water table. If you can either keep the water table to a constant level somehow by using of drainage techniques where you drain water out of the soils, and given the fact that these are clays, that's always a challenge to do that. But if you can do that, if you can reduce the amount of swinking and shrinking and swelling, then you're very much ahead of the game. And actually there are good reasons for, I think, virtually every foundation, particularly if you've got a high water table. There are other reasons why, as well, why you need to keep water away from it. Beld bases for drill shafts. We talked about beld bases, and we talked about the fact they were strictly for clays. And we talked about the fact that they can be used to not only improve the toe resistance of it, but also to resist uplift. And if there's one thing you get with an expansive soil, it's uplift. So you want to prevent uplift from happening. Now we turn to estimating the upward load capacity of beld shafts. We're talking strictly about that area between the diameter of the shaft and the diameter of the beld. And the upward load capacity is simply equal to that projected area times the average undrained shear strength of the cohesive soil between the base of the beld and 2 BB above it, and that times some bearing capacity factor. The bearing capacity factor depends upon whether the clay is unfissured or fissured, and you can see that it varies by a factor of 5, so that's not an insignificant question. So, and that's just for the uplift of the base. It doesn't include the shaft resistance, and we're always talking about uplift. What we're trying to do with the beld shaft is to resist, say if you've got a foundation on an expansive soil at the top and it is pushing against the foundation, the beld shaft, the idea is to give uplift resistance against being pulled up by the structure and the drill shaft, along the drill shaft. So this is the use of a deep foundation to counteract the effects of uplift. And we have an example here. We have a stratum, and buried fairly deeply into the bottom stratum is a base. The base has a diameter of 5 feet, and the drill shaft is 2 feet. So we've got a fairly substantial size of a bell here. We want to find the uplift. The factor of safety is 5, which is typical for uplift. The very stiff clay is fissured and include the weight of the foundation. So what we do is we start by computing using O'Neill and Reese's method to compute and by the way, they came up with the bell shaft thing too. The O'Neill and Reese's method for the shaft friction, and this done exactly the same way. You have, again, keep in mind, you've got 2 exclusionary zones. The first exclusionary zone is the 5 feet at the top. We throw that out. The bottom exclusionary zone is different. It is equal to twice the diameter of the bell toe. The bell toe is 5 feet, so therefore we have a 10-foot region at the bottom, and you can see that. So therefore, the top layer is zeroed, and the bottom layer is 0. So we take the rest of the shaft, we apply the formulas exactly the same way as we do with O'Neill-Reese methods for clays. We're talking about clays now. And we compute the friction. Now the shaft friction is not only shaft friction, unlike regular compressive unbelled toe resistance, is able to resist uplift as well as downloading as well. So we get a F of S times the A of S. We go through, get a little F of S, multiply by the area of each of those layers, and we end up with a total shaft resistance of about 340 kips. And that's just the frictional result of the shaft. We haven't gotten the uplift capacity. The next step is the uplift capacity. We take our formula and basically we perform basic plug and chug. We've computed the nth of U for the bell here, however, and it's equal to 0.7 times the diameter of the bell over, let's see, hang on a minute, let me make sure I get this. The diameter of the embedment into the bearing stratum, excuse me. The diameter of the embedment of the enlarged base into the bearing stratum over the BB, which is the diameter of the bell. And so therefore, the deeper the bell is embedded into that stratum, the higher we would expect the bearing capacity factor and the more load that they can take, which is what we would expect. So we plug and chug those, we get 3.29, and since they are less than 9 is the maximum value you can have for nth of U, we leave it at 3.29. So all we do is we take that, we plug in, and we chug, and we end up with P upward A of 217 kips, which, considering that the shaft friction only at 340, is a considerable addition to it. Then we compute the weight of the foundation. I said drill shafts traditionally ballast, particularly in uplift loading. They work for you in uplift loading, they work against you in downloading. And in uplift loading, they can ballast the foundation, just like a very heavy shallow foundation can do. So you add that weight, you add the weight of the entire shaft down there. We kind of took a quick and dirty shortcut here at WF, the weight of the foundation, and essentially we averaged the diameter of the shaft and the diameter of the bell together, and basically assumed that the weight of this is a cylinder of the average diameter. We did that. We plugged and chugged again with 0.15 being kips per square foot or cubic foot of concrete, and we end up with 34.5 kips. Then we take all those, we put them together. There is another degrade factor, and that's just 0.75. And that 0.75 represents a degrade for uplift. We are assuming that a shaft friction is not as effective in resisting being mobilized in uplift as it is in down. It is going down. So we multiply that shaft with about 0.75. There are some people who would probably say, well, we should take the weight of the foundation out of the factor of safety. But in this case, we won't do that. And so we just add them all up, divide them by 5, and we get 101.4 kips as our final result. Notice we've used a factor of safety of 5 for uplift. That concludes this series of lectures for this part of the course. And until next time, thanks for watching, and God bless.